Hello everyone, and thanks for watching Edupedia World Videos. In the previous video, we learned about concepts of center of mass, and in this video, we learned how to apply concepts of linear momentum and other useful concepts to systems having more than one particle. Right? So let's take a brief recap of what we did previously. We saw two formulas for the position vector of the center of mass of a composite system. One was for discrete systems in which you have a lot of point particles, and that was summation I MIRI divided by summation MI. So the x coordinate would be m1 x1 plus m2 x2 plus m3 x3 and so on, divided by the total mass. Similarly for y and z coordinate. For continuous systems, it was integral of dm times r divided by integral of dm. So the x coordinate would be integral of dm into x, the y coordinate would be integral of dm into y, and so on. Right. So what we need to do right now is, we've seen center of mass, but let's say we want to find out. Let's start with the simplest case. We have three particles, m1, m2 and m3. And let's say they have position vectors r1, r2 and r3. They have velocity vectors v1, v2 and v3 and acceleration vectors a1, a2 and a3. Right. So the position vector of the center of mass will be m1 r1 plus m2 r2 plus m3 r3 by m1 plus m2 plus m3. Right. So let's say the center of mass is initially at this point, and let's say this object is moving in this direction, this is moving in this direction, this is moving in this direction, with velocities and accelerations. Obviously, if the particles have accelerations, there must be external forces acting on the particles. Right. So what is the velocity of this point? That is simply the derivative of the upper equation, that is derivative of RCOM by dt, and that will give me, since all the masses are constant, it will give me m1 dr1 by dt plus m2 dr2 by dt plus m3 dr3 by dt by m1 plus m2 plus m3, and dr by dt is simply v. Right. So this is m1 v1 plus m2 v2 plus m3 v3 by m1 plus m2 plus m3. Similarly, we can find the acceleration of the center of mass. That will be derivative of the velocity of center of mass with respect to time, which will be m1 a1 plus m2 a2 plus m3 a3 divided by m1 plus m2 plus m3. Right. But what is m1 a1? m1 a1 is the net force acting on particle 1. Right. That includes the external forces as well as internal forces. And we know by Newton's third law, let's say these two objects have a force Fa towards each other, these two have Fb towards each other. These are internal forces, and by Newton's third law, they are equal and opposite. Similarly, these are F3. Right, don't pay attention to the figure, it will get slightly messy. These concepts are what are important, right? So I'll just write it here. M1 A1 is equal to F1 external plus two other forces, Fa and Fb. Right, sorry, this should be Fc. Right, M1 has three forces acting on it. The net external force, plus obviously M1 cannot apply a force on M1, M2 is applying a force on M1 and M3 is applying a force on M1. So plus Fa plus Fb. A, B and C are internal forces, right? Similarly, M2 A2 will be F external plus this, M3 A3 will be this, plus, but this Fa and this Fa will add up to 0. Right? So this basically implies that m1a1 plus m2a2 plus m3a3 is equal to f1 external plus f2 external plus f3 external. And this is a result which you have actually seen before, that summation f external is actually equal to summation f external plus summation f internal, because summation f internal is actually 0. Now remember, summation of f dot dx need not be 0, because even though this fb and this fb are equal and opposite, these two displacements are not equal, right? So fa this plus fa this will be 0, but fa this dot dx1 plus fb this dot dx2 will not be 0. So, and that we've seen before, that internal forces, though they add up to 0, they can do work, right? And we defined the work done by internal conservative forces as the negative of the change in potential energy. So the sum of all the internal forces is 0, which simply means, if I look at this equation again, ACOM is equal to summation F external by the total mass m1 plus m2 plus m3. Right? I'm going to remove this now. So that gave me a very nice result. Summation F external is equal to capital M A CM. Now this is where we see the true power of center of mass, right? Because remember, our starting point in these lectures was when we started in the previous lecture was this simple problem. I have an object of mass m1, I have an object of mass m2 going towards the right with an acceleration a, coming down with an acceleration a. I did not want to take these particles individually as a system. I wanted to take this combined thing as a system. So in this combined thing, I would add up all the forces. Actually, this tension will cancel with this tension will cancel with this tension. This normal force will be there. This normal force will be there applied by this surface. The gravity will be there on this. So there will be a number of external forces on this system. This is my system now. So in this system, I can write the sum of all the external forces. That will be equal to m1 plus m2 plus the mass of the strings, which is 0, plus the mass of the pulleys, which is 0, multiplied by a particular acceleration. What was that acceleration? That is what we needed to find out. So that is nothing but the acceleration of the center of mass. And we can calculate that. In this case, it will be m1a plus m2a divided by 2. So it will be basically m1 plus m2 by 2 times a. Right? So this is a very important formula. And this is what we wanted to find out. Now, remember, when we are doing Newton's laws of motion, we had some restrictions. One of those restrictions was in choosing a system to make an FBD to write equations of. The first step was choosing the system, and you could only choose systems in which every particle had the same magnitude and direction of acceleration. That is no more a restriction. You can choose a system in which different particles have different accelerations. All you would need to do is you would need to take the acceleration of the center of mass in the equation, right? And that was the confusion before, that if we were to take a system in which different particles have different accelerations, we could take the sum of all the masses to be the total mass. What would we write the acceleration to be? So the acceleration would be the acceleration of the center of mass. Similarly, let's look at the other equation. We saw VCOM is equal to m1v1 plus m2v2 plus m3v3 by m1 plus m2 plus m3. What is m1v1? It is the momentum, linear momentum of the first particle. By the way, I occasionally say linear momentum because we'll see another type of momentum later, which will be angular momentum. But for now, when I say momentum, you can assume it to mean linear momentum, right? So this is equal to actually P1, momentum of the first particle, plus P2 plus P3. And what is that equal to? M times VCOM. M is the total mass, m1 plus m2 plus m3. So we get another result, summation P is equal to m VCOM. So again, if we have a system in which different particles have different positions, velocities and accelerations, We can find the individual momentums and add them up, or we can simply find the velocity of the center of mass and multiply it by the total mass, and that will give me the total momentum. Right? So these two formulas are basically why we see the concept of center of mass is very important. Now we can treat systems in which different particles have different velocities, accelerations, positions, and we can treat them as one combined system as long as the mass is the total mass, and the point which we focus on, instead of any individual particle of the system, we focus on the center of mass, and everything is related to the center of mass. Right. Another important use of the center of mass is, we saw the potential energy of gravity, we derived it to be mgh, right? But that was for a particle. Let's say this is my ground and I have a rod of total length L, and I want to find out the potential energy of this rod, the gravitational potential energy. The easiest way to do would be to take individual elements, find out their potential energy and add them up. So let's do that. Let's take an element of thickness dx at a height x. The potential energy of this will be dm times g times x, right? And dm can be written in terms of dx, and we'll integrate this. But what is dm times x? Dm times x is nothing but the total mass multiplied by the height of the center of mass, right? Because integral of dmx divided by m was x of center of mass, in this case the height, right? So this is for a single particle, capital mghcom, for an extended body. So you can try to find this by integration, but I can see directly that if the length of the rod is L, the center of mass is at the center L by 2. So the gravitational potential energy in this case is mgL by 2. So this is another important result. If we want to find out the gravitational potential energy of an extended object, we can simply find the height of the center of mass, and we can assume that the whole object is of mass m situated at the center of mass. Right? So now we've seen some few uses and some few definitions, for example, velocity and acceleration of center of mass. We'll now move on to the principle of conservation of momentum. Right? So let's take the most basic case, two objects, two particles, mass m1 and mass m2, moving towards each other under their mutual attractive forces, right? Let's say the gravitational forces. So this is F and this is F. The magnitude is the same, the direction is opposite, right? What is RCOM? That is M1 R1 plus M2 R2 divided by M1 plus M2. It'll probably be somewhere in the middle. Similarly, VCOM we know. I'll just write ACM directly because that's what is important right now. ACM will be M1 A1 plus M2 A2 by M1 plus M2. But that is equal to 0 because we are assuming there is no external force acting on the system. We are assuming we have two particles which are moving towards each other due to their mutual gravitational attractive forces, right? So then M1 A1 of this particle is equal to this force, and M2 A2 for this particle is equal to this force, and by Newton's third law the sum of these forces is 0. So ACOM is equal to 0. But what is ACOM? Is equal to d of VCOM by dt, which is 0, which implies that VCOM is a constant, which implies that the total mass times VCOM is constant. So summation Pi, which is the total momentum of the system, is a constant. And this is the result which is called the principle of conservation. This is very important, of linear momentum. And it simply states that if summation F external is equal to 0, that is, if you have a system in which no external forces are acting, only internal forces are acting, then the net linear momentum is a constant. So of course, if I drop an object from a certain height and let it fall towards the ground, linear momentum is not constant because external force of gravity is acting. But if two objects are moving towards each other, we can see that even if they're at rest, later they'll have some momentum, some speeds, then some higher speeds. So the momentum individually would have greater magnitudes, but they'll have opposite directions. And the net momentum will always be constant. If both of them were at rest initially, the net momentum will always be zero because it was initially zero. Right? So this is an important concept called the principle of conservation of momentum. Let's see a couple of examples of this. Let's say there's a plank on a floor. Right, this is the floor, slippery floor, no friction at all. And there is a man standing on the plank. Right, the mass of the plank is capital M, the mass of the man is small m. Right, and the man moves towards the right with a speed v, small v. Right, and between them there is friction. So we'll consider this complete plank plus object, plank plus man to be the system. Right, so if we consider the man plus the plank to be the system, the friction acting between these two will become an internal force. Right, and if this man is walking towards the right, he's having a frictional force towards him to the right. In return, this plank will have a frictional force towards the left. They'll be equal and opposite by Newton's third law and will add up to 0. And since this plank is frictionless, this ground is frictionless, we'll take this complete system and there is no external force acting on it in the horizontal direction. In the vertical direction, there is gravity and normal and they cancel out. So in the horizontal direction, the net momentum will always be 0. Right, if initially it was 0. So initially the man was standing at rest on the plank. Then the man starts moving with a velocity v towards right and the plank will have to recoil, right? And what is the velocity with which it will recoil? So initially the momentum was 0. Finally the momentum is mv plus capital MV. So v equals minus mv by capital M. Right, so this moves towards right with v, this will move towards left with minus mv by M. Right, simple enough. Now there's a slight variation to this problem which makes it a little bit tricky. So let's see that. And it involves the concept of relative motion which we've seen before. So in this case, this speed v is relative to the ground and this speed v is also relative to the ground. That means I said that the man is moving towards right with the speed 10 meters per second relative to this ground. But it's often, since the man is standing on the plank, it's much easier to measure the speed of man with respect to the plank. Right, so let's forget this question for now. Let's change the question slightly, and now the question is, this speed v is with respect to the plank. Right, so let's assume the speed with respect to the ground is u. Right, and the speed with respect to the plank is v, and the speed with respect to the ground of this is v. Right, so speed of man with respect to plank will be speed of man minus speed of plank. Right, so v, which is speed of this man with respect to the plank, will be u, speed of this man, minus speed of the plank. Right, minus, but this will be minus capital V. Right, because it's in the opposite direction. So it will be u plus v, or actually we can just write v is equal to u plus v because they're all in the same direction. Right, so in this case capital V, it will be minus m. Now this v was with respect to the ground. Right, so it will be minus u by m, but we don't know u, we were given v. So v is u plus v. Right, so u is small v minus capital V. So it will be minus m small v minus capital V by m. So easy enough, right? So what generally they do is, instead of giving the speeds with respect to the ground, which will make it quite easy, they'll give it with respect to the plank. So the first step seems tricky, but all you need to do is assume all the speeds with respect to the ground and with respect to the plank to be different variables, and just write the simple equation of relative velocity. That is, the velocity with respect to the plank is the velocity of the man minus the velocity of the plank. Right? So this completes conservation of linear momentum, and you can have a lot of problems like this. For example, the standard problem which is used is, this is a pretty simple gun. I apologize for that, but this is a gun and the gun shoots a bullet at a speed, let's say 1 kilometers per second, and the mass of the gun is 1 kg and the mass of the bullet is 5 grams. So if the speed of the bullet is 1 kilometers per second, and in the question it will be given whether it's with respect to the ground or with respect to the gun. Let's assume with respect to the ground for now. So if this bullet moves at a speed of 1 kilometers per second, then the gun experiences a recoil velocity. Why? Because if we take this combined thing to be the system, there is a nozzle in the gun which pushes the bullet, but it pushes the gun back as well because of Newton's third law. So the gun will recoil with the speed, and you can find that by using the fact that the linear momentum initial is equal to the linear momentum final. Right. So anytime you take a system in which there is no external force acting on it, the linear momentum of the system has to be a constant, and this is called the principle of conservation of linear momentum. Right. In the next video, we'll use concepts of conservation of linear momentum to tackle a very specific and interesting problem, the problem of collisions. Right. So thank you.